Hello again. Welcome back. In our last few lectures, we've talked about the entropy of some artificial languages. Well, what about the entropy of a real language, a natural language like English? That's a little harder to figure out. First of all, let me observe that in the standard encoding of English, that is, letters on a paper or, words that you speak, there's a lot of redundancy in that encoding. Okay? So, for example, take a look at this text at the bottom of this thing. I've taken all the vowels out of it, and yet most people can still read this text with no problem. What does that suggest? Well, it suggests that there's a lot of redundancy in the encoding, because if you can remove some stuff and still extract the meaning, then the encoding has to be redundant. And so clearly the entropy of English is less than what you would naively expect from just looking at a standard encoding. Okay, here's another one. Right, somebody sent me this this text, and the letters are all rearranged within the words in the text, and yet most people can still read this thing. So once again, that suggests that not only is the presence or absence of individual symbols redundant in some sense, that even the ordering of letters within words is redundant. And spammers actually count on this pretty heavily, because if they sent you an ad for Viagra, your spam filter might, get rid of it. On the other hand, if they send you an ad for Vigera or something like that, maybe it gets right through, but you know right away what they're trying to sell you. Okay, so how might you go about figuring out the entropy of a natural language? Well, in English we use 26 letters and a space, lots of other letters as well, but or characters as well. But let's just, be minimalist about this. So suppose that we were going to encode English using 26 letters and a space. Well, a very naive encoding would be just assume that all letters and spaces are equally likely, and just apply that, our entropy formula, to that. So then we would say that the entropy of the language is just log of 27, log base 2 of 27, which is 4.75. What that would suggest is that you can't do any better than 4.75 bits per symbol in encoding English. But this is a pretty naive model of English. This is called the zero-order model of English, and you can apply a zero-order model to any language. So the underlying assumption here, that all symbols are equally likely, is clearly false. And so let's go to the first-order model. The first-order model says, well, we're going to look at the likelihood of various letters within the English language, and here's a chart which gives those for average text in English. So you'll see, for example, that E has a probability of about 13%, almost 13% in English. What does that say? It means that if you look at a very large volume of English text, you can expect E to be pretty common. About 13% of the letters will be E. On the other hand, Z, much less than 1%. Right? It's exactly what you would expect. And so if you apply our formula and plug these probabilities in, you'll see that you get an answer for entropy of about 4.219 bits per symbol. This is the first order model of English. Okay, so we've got the zero order model and the first order model. What do you think would be the second order model? Well, it takes into account the likelihood that a particular letter will fall after another letter, right? So in the first order model in the zero order model and the first order model are what we call zero memory, because they assume that each letter is independent of the context. And that clearly is false as well, right? So in English, it's much more likely that, say if you see a Q, you're pretty sure the next letter is going to be a U. And if you see an E, the next letter is many times going to be an N, much more likely than, say, an X. And so we could look at digrams, which is pairs of letters, or trigrams, which is triples of letters, and so on, and we could factor that into our computation of the entropy of English. And if you do that, you get the second order model with digrams and the third order model with trigrams, and so on. And somebody has done this work, and they figured out that the third order model of English yields about 2.77 bits per symbol. Now, how far can you carry out this process? Well, until you run out of steam or energy, right? But no one actually knows what the entropy of English is, because there are so many factors that go into the figuring out these probabilities. But Shannon, Claude Shannon, again the guy that came up with this whole theory, did some experiments based on asking people to fill in missing chunks of text, I think, and he came up with an estimate that English actually has an entropy of somewhere between 0.6 and 1.3 bits per symbol. Now what that says is that each letter in an English word really only conveys about 1 bit of information. And that really is pretty amazing, I think. Okay, so what have we said? Well, we said that all natural languages have a lot of redundancy. And that's really what helps you understand when somebody is speaking to you. If they didn't have all that redundancy, you'd have to listen very carefully, or you'd miss most of what they're saying. And computing the entropy of a natural language is much more difficult than these artificial languages that we've looked at. It can be done, but it requires some very sophisticated models, and you probably can still only get an estimate of the entropy of something like English or Japanese or Urdu, say. Thank you.